Okay, guys, we're going to get started right away. Miss Marcus and I, we love this unit because we feel like we finally get into the real chemistry of it. I'm finding little happiness of virtual learning, like hair that doesn't have to get fixed, makeup doesn't have to go on, and I get to represent my alma mater. So, hey, good stuff. All right, chemical reactions. So I'm going to take you through today with understanding what a chemical equation looks like. By the end of this lesson, you're going to have hopefully a pretty good feel on how to balance a chemical equation and why we do that. And throughout this unit, you're going to continue to get practice with nomenclature. So if you felt like you didn't do so well on the exam that we just took, remember you're going to get 5 weeks of a lot of practice with this. Okay, it's not something that we stop doing. So we're going to get going right away. You need your guided notes available to you for this. And with that, whenever we look at the very first thing, parts of an equation, this is what we're looking at here. So this whole thing is called a chemical equation. That arrow, this little arrow is going to show something in a second. If we were to look on the left-hand side of a chemical equation, we call those substances reactants. So reactants are going to combine together, and sometimes they make one product, sometimes they can make more than one product. But anything on the right-hand side of the arrow are called products. Okay, again, it could be one or it could be more than one, doesn't matter. And then this arrow that's here that is being pointed to with another arrow, that represents that it produces or that it yields. So we don't say that calcium and chlorine equals these products. We would say that calcium and chlorine yield calcium chloride. Okay. So the arrow means yield. So you're going to get some introduction into some language today of what it is that we're talking about. Remember, it's self-paced. At any point, you can pause to push things out, but I am not going to slow down just for you to be able to push pause to get your notes filled in, okay? So some pieces of an equation that we need to be familiar with whenever we see these in a balanced equation are and they're all going to be written as subscripts minus this triangle will be put in a different spot, and then obviously the arrow we just talked about. But all of these will be written as tiny little subscripts off to the side. Normally, when we see a chemical formula, we'll see it to the bottom and to the right of that chemical formula to tell us a little bit more about those substances. So if we see a tiny little S written there, it's going to tell us that it's a solid at room temperature. If we see a tiny little G, so a subscript of G written there, it's going to tell us it's a gas. If we see a L, that'll tell us it's a liquid at whatever it is we're doing. So that reaction is in a liquid state, or that substance is. AQ is going to be possibly new for us. So AQ means aqueous, and maybe off to the side, because aqueous might be a new term for you. Probably off over here, you might want to write dissolved in water. It's really trying to tell you it's a solution. So it's a solution that is dissolved in water as a solvent. Okay, so we might see aqueous there. If we see a little triangle, and a lot of times that triangle will be written on top of the yield sign, on top of the arrow, that means that heat might need to be a catalyst, it could be, or maybe heat is released, could be another way, or maybe heat is needed. So we might see a triangle at times for heat. And then again, we already wrote this up above, but just remember that the big arrow that we'll see between reactants and products is telling us that it yields or it produces something, okay? So these are all things that an equation can tell us. We're going to go through, what can an equation tell us? And then also, what are some things an equation cannot tell us? So besides it just telling us the state of matter of the reactants and the products, an equation could also tell us if a catalyst is used or not. So if a catalyst is used, and let's just look at this. This is just a normal reaction, normal equation. So here I've got my reactants. On the right side of my yield sign, I have my products. This happens to be the equation for hydrogen peroxide. So hydrogen peroxide decomposes into water and oxygen. And this would just be written like a normal equation. Now, right here, I would say that a catalyst is not used. Okay, and you're going to see the difference whenever I'm showing a catalyst is used. If a catalyst is used, we see the catalyst written on top of the yield sign. So this would be an example of saying, yep, this decomposes. And by the way, a catalyst, in this case, manganese dioxide, is used for this reaction to occur. So what is a catalyst? If you need a review for that, it's something we talked about in FISI, but quick review, it's something that makes the reaction go faster. And it's not consumed during the reaction. So manganese dioxide is just like a platform to help this reaction occur quicker, but it's not used up in the reaction. It's not a reactant. It's not a product. It's more like a landing dock to help a reaction occur a little bit quicker, to let the reactant turn into products. So this would say that a catalyst is used. If I don't have anything on top of that arrow, it would tell us that a catalyst is not used. So that's something else that a reaction can tell us. But there's also things that a reaction cannot tell us, okay? So one of the big things that a reaction can actually not tell us is if the reaction will actually occur or not. Okay, we have no idea if that reaction is actually going to occur. Just because we can write it down does not mean that the reaction is going to happen. And probably a really good example of this would be this equation right here, okay? So CH4 is the chemical equation for methane gas. And we know that methane gas should combust with oxygen, but that reaction will not happen if we don't have an appropriate catalyst. Okay, so I'm going to just change my screen a little bit, where I think you guys can see, if you look down here, it's in the corner of your screen, but right here, this is the gas outlet valve. Let me move it down just a tad more. So that natural gas valve sends out methane gas. Now, I could turn this on. We can hear it going, but that does not mean that immediately I'm going to see a flame coming out. There's oxygen in the air, right? So there's oxygen, everywhere all around us. But just because I allowed methane and oxygen to react, or to mix, I should say, I shouldn't use the word react. Just because they're mixing together does not mean that that reaction is actually going to occur. What would be needed for that reaction to occur? Think back when you guys were practicing lighting a Bunsen burner. You have to have a spark. You have to have really what's called some type of activation energy for this to occur. So even though I could, on a sheet of paper, write down what the product should be, it doesn't mean that it's going to absolutely happen or happen spontaneously. Okay, just because we can write it down doesn't mean it is going to happen. We got to make sure, does it actually have the activation energy or whatever's needed for that to occur? So this would be one thing that a reaction does not tell us. What else could a reaction not tell us? It doesn't tell us the degree to which a reaction goes to completion. Not all reactions go to making all products. In fact, very few reactions go to making all the product. A lot of them are going to stay in some balanced state, okay? Having some reactants left over and then some products. So just because I can look at a reaction, I have no idea how much it's going to actually go to completion with that reaction. What else? It does not tell us the actual path a reaction goes through in order for the reaction to occur. This is something that if you continue to learn chemistry and take chemistry in college, or even play with, they maybe do this in AP Chem, but in your first year chemistry class, probably second semester of your first year freshman college chemistry, you will learn what's called reaction mechanisms and how the reaction actually occurs, how the electrons move in that reaction for the products to be made. Looking at a general chemical reaction does not tell us the mechanism by which the reaction occurs, okay? Okay, so what our big goal, like our math practice goal today, is going to be to actually learn how to balance an equation. But before we learn how to balance an equation, we probably should ask ourselves why. Like, why do we even bother with all these numbers and this math to balance an equation? And it really comes back to this. So due to the law of conservation of, and this is mass, due to the law of conservation of mass, we know that matter cannot be created or destroyed. So if we know that, whenever we're communicating the mathematics of a chemical reaction, we need to honor that law. We have to show in the law that we cannot create matter, we cannot destroy matter. I cannot say if I began with 2 hydrogen atoms, all of a sudden one of them vaporized. Like, we need to honor this law in that chemical reaction and show that. And we're going to show that with things that are called coefficients. So that's what we mean by how we can illustrate this by balancing an equation. I'm going to do this with a demo just to have a little proof for you that we cannot create matter, we cannot destroy matter. So down there at the bottom of the first page, on page 1, take a moment to, just for now, to write out the equation. So what I'm going to do is I'm going to take lead nitrate, and it's going to be in aqueous form. Both of these are. I'm going to take potassium iodide, which will also be in aqueous form. And these are the two products that are going to be made. So we're going to end up making lead iodide, and then we're going to make potassium nitrate. Before we do that, once you have this written out, push pause for a second and just see if you can do a mental note of what are the coefficients and then what are the subscripts in this reaction. Subscripts you should be a little familiar with because we did that talk with chemical formulas and the nomenclature. Coefficients, maybe you're going to have to think a little bit. So try it, write this down, do a little mental note. What are the coefficients? What are the subscripts? And by the way, that's a comment that shouldn't be there. I don't even know. That was a typo. So ignore whatever that thing is right there. Okay. All right, hopefully you pushed pause and you really thought about this. You came back, but what you would find is these are the subscripts, right? And then these are the coefficients. So this might be the big number 2s. Those are going to be things that we're going to learn how to do today and the why behind it. The subscripts are things that you played around with already. Okay, whenever we did the naming and chemical formula writing. All right, so I'm going to switch my camera and let you see what I've got here on the table. So I've got a balance in front of me, and right now I've got nothing in the beakers. I'm going to take some lead nitrate, and I'm also going to take some potassium iodide. And with those, and they are, if you take a look, they're in a liquid form right here. So I want them to start off as a reactant state. So I'm just going to take some lead nitrate, and I'm going to put it in here. And then I'm going to do the same thing with potassium iodide. So potassium iodide is an aqueous solution. We buy it as a salt. So remember, a chemist for salt, it's not just sodium chloride, it's any ionic compound. So we buy it as a solid salt. It's aqueous, so it'll dissolve in water. So we mix it with water, and we end up with these solutions. So right now, and remember what the purpose of this demonstration is, to help you see that whenever we have a reaction, we don't lose mass. So those particles and those atoms are going to get rearranged, but we don't lose mass. So let's see if we can prove that. So I'm going to put all of these things on the scale. All right. To think backwards when I'm looking. And if we do a look, this is pre-reaction. So this is actually seeing anything going on, which you guys, maybe it's looking like you might be struggling seeing a number on that scale. So hold on one second. Okay, I think you can see something now, which I know you can't now see the beakers, but we see 114.7 is what you should register. And I don't know how well, maybe you can see that now. So 114.7. All right, so what I'm going to do now, well, first I'm going to get her not as bright anymore. I'm going to take these two chemicals that are now the reactant state, and we're going to mix them. Then we'll put those test tubes back in there, and let's see if I can do a new, and definitely a clue of a chemical reaction, right? This is something Ms. Marcus is going to talk about tomorrow. But that reaction happened, and if you notice on this, I just, maybe by error or something, I just lost a tenth, but it did say at one point 114.7. And who knows, maybe my scales having a little sass moment. But we aren't going to lose that mass just because a reaction happened, okay? So the law of conservation of mass, whenever we do these balancing equations, we have to honor that information. We have to show that we will not lose or gain mass. I'm going to go back, switch my camera so we can come back to this. But just, a little bit of fun here. So this product that was made, that's a lead iodide. And maybe you've heard a little history that, lead used to be found in paints. And the reason why is lead makes, look at how beautiful it is. That's a very bright yellow. Lead makes gorgeous colors. The ancient Chinese used to use lead paints on their face. Whenever you see some of those real pretty past pictures of how ladies would decorate their face, they would use a lot of lead-based paints. Not the best choice for their health, but it was definitely beautiful with what they could come up with. So in this particular reaction, the thing that we're seeing as the impact is this lead iodide. So lead iodide is a yellow solid that is created. The potassium nitrate is actually soluble. It's still aqueous in the solution. It's boring. It doesn't look too different than how we began, but it's that lead iodide that gives us the clue that we have a reaction there. So what we're going to learn how to do is this coefficient balancing. So I'm going to take you through something that's a little, it really breaks down the steps, and then we're going to do practice together with it. Okay, so if you looked on the next page of your notes, it says that first thing, if we're going to try and balance an equation, so in order to write the correct balanced equation, there's a little trick you have to know. And there's a few elements on the periodic table, and we'll talk about the why when we get into bonding. But there's a few elements on the periodic table that, they're kind of like those people, and I am going to pinpoint, probably mostly girls, that tend to love to go to the bathroom with another buddy. Like, do you ever have like that friend that she has to go to the bathroom and she's like, come with me. They can't go to the bathroom by themselves. I don't know. I call them diatomics because there's these elements that are the same way. These certain elements you'll never find by themselves in nature. They're always bonded with another atom of the same type, and they're called diatomic. Di meaning two, so two atoms. So these things, if we realize they're by themselves, like oxygen by itself, like I never say, hey man, give me some O. It's always give me some O2. You're in a hospital setting, you always hear O2. So oxygen is one of these diatomics. They exist as a pair, and we'll learn later why in bonding, but it's to increase their stability in nature. So what are these? We're not going to draw them out. We're just going to list them out, and you're going to see me write it kind of funny. We could write it like this, and some science teachers say there's this really weird scientist named Brinkelhoff, but that's kind of a funny way to remember. So Brinkelhoff is one way to remember what they are. But if you look on the periodic table, and I'm going to spin you around just for a second. Okay, so if you come over here and you look at the periodic table and you see what they are all of these halogens. So these are halogens, fluorine, chlorine, bromine, and iodine. All of those are diatomic in nature, plus it's hydrogen and nitrogen and oxygen. So it's hydrogen is diatomic, nitrogen, oxygen, and then all of these halogens. Now, astatine is really radioactive, so I kind of ignore that because astatine's not going to really do much. It's just going to decay anyway. So if you're more of a visual person, you can think like this. You could think H for heck. So heck, and then watch over here. Heck no, just spells out the word no, nitrogen, oxygen. Heck no, and then all of your halogens. So heck no halogens is another way to remember which ones are diatomic. So you can either think Brinkelhoff, or you can think heck, again, looking at periodic table, heck no, and then all of your halogens, okay? So why is that important? If we are being told in a chemical reaction that any of those elements are involved, then we have to make sure whenever we're writing out the balanced equations, we have to put a little subscript of 2 there. They're never allowed to be by themselves. They're those folks that when they go to the bathroom, they always bring a buddy with them. So we have to pay attention to that. We have to honor that. So eventually we'll do some problems where we see that as an option. Here's a practice one right away. So whenever you see oxygen, why is there that 2 there? Well, Brinkelhoff, it is a diatomic, or heck no halogens, however you want to remember it, but it's a diatomic. It can never exist by itself in nature. So whenever we're asked to balance an equation, we're only going to be allowed to add what's called coefficients. We'll never be able to add extra little subscripts to balance. We'll only add coefficients. And these set of rules kind of break up how to do this. I'm going to go through it again, and I really think that more practice you get, the better. But this gives you kind of a written set of how to do this. Step one would be to count the number of atoms on the left and then the right-hand side. So that's what you see us doing here. We looked at mercury. We have one mercury. We have one oxygen. On the right-hand side, one mercury, and then two oxygens. So when I evaluate that, I'm recognizing, or I need to recognize, oxygen's not balanced. So there's things I have to do to balance it. What I'm not allowed to do is I can't put a subscript down here. I'm only going to be allowed to put those really big numbers that are called coefficients. Okay, so that's kind of what we get to next. So balance each element using whole numbers that we're going to call coefficients. And just a hint, sometimes it's best to try and balance the compound, and then we worry about balancing a standalone element. So just something to think about. So as we look at this, we already realized that oxygen was a problem. So we put this number 2 over here by mercury oxide, really mercury 2 oxide, because we recognized that we had to do that. Now, in doing that, though, it kind of made a mess with mercury, right? Because it impacted now we have 2 mercuries. Yeah, it fixed the oxygen, but notice that we have to put a 2 over here then by mercury because, again, I cannot destroy mercury, okay? So it just broke up. It broke it up into 2 separate mercuries. So, and that's what we're saying here, that the mercury atom needs balancing on the product side. I'm going to go through an example. I think this sometimes can be a little confusing in the notes. You're going to be like, oh my gosh, wait, what? Pause. I'm going to do the examples with you, and I think you're going to pick it up, okay? Then whenever we're done, because sometimes, especially when you're brand new at balancing, you kind of get all excited, you start balancing, and you keep adding more and more coefficients, and you go back and you look at it, you go, hey, awesome, it's balanced. 4 mercuries, 4 mercuries, 4 oxygens, 2 times 2, 4 oxygens. And then if you really look at this, you go, oh, shoot, that really needs to get reduced down. So make sure your final coefficients are always in the least common multiple form, the lowest ratio. So 4, 4, and 2 really needs to reduce down to 2, 2, and 1. As you get better at this, you won't accidentally make that mistake, but sometimes whenever you're first practicing, you end up making that mistake. So always make sure that it's in the least common form as far as a ratio. Okay, so I find that it looks a little better on the screen. I'm going to turn off the screen as soon as I find my things to do that. And let me pull this up. And let's start with that first problem that's right there. So, and here's where you have to think. So all the problem reads is hydrogen gas reacts with oxygen gas to produce water vapor. So you have to be thinking right away, when you write these elements, you got to think Brinkelhoff. And so we got to go, okay, hydrogen, that's right. That is a diatomic, Brinkelhoff, heck no halogens. So, and because it gave me states of matter, I want to include that as well. So hydrogen gas plus, and then it says plus oxygen gas. So oxygen Brinkelhoff, it's diatomic. I'm going to write a little g because it's in a gaseous form, is going to produce, and it told me it produces water vapor. Okay, so vapor means gas. Okay, so let's just have a little fun with this. I have these guys just to let you see what's going on, and I'm going to use these to represent what we have. So let's let this represent our hydrogen. We'll let the blues represent that. We'll let the reds represent our oxygen. Okay, and it tells us that we're trying to make water. So if we're trying to make water, and I'm going to show you just a little bit of a different way that we can write this out. So we have hydrogen, and what I would do is write the 2 elements right in the middle of the arrows so that you can see, and you don't have to write the elements twice then. So if we look at our beginning, we have 2 hydrogens, we have 2 oxygens. If I count over here, I have 2 hydrogens, I only have 1 oxygen. So these reactants are going to try and form water. Okay, so let's take what I did with this demo, but let's take it down to just a really slow modeling level. Okay, how does it make water? Well, it needs 2 hydrogens and it needs 1 oxygen. Okay, so that has made a water, which is great, but we have a problem, right? I have a leftover oxygen over here, and how am I going to solve that? Okay, well, I'm going to solve that by adding more hydrogen. But remember, hydrogen does not just go in singleton forms, right? I have to add a whole nother one of those particular elements, and it's diatomic. So I have to add a whole nother one of those. So whenever I add a whole nother one of those, I probably, and I'm just going to show it this way, and then I'll show you another way we can do this too. That means that I went from using just one to using two. I still only used one water or one oxygen, right? So now, if I'm trying to make my product and I want everything, as I balance this, I need everything to line up kind of nice here on the right. Now that got rid of all my reactants. I made all of my product. But what did I really make? I really made 2 waters. Okay, so that's the essence of what we're doing at a chemical level. But that does not mean you have to draw all these models every time. So what I'm going to do right now is take this same example. I'm going to go back and I'll show you math-wise how we're going to come up with the same answer. Okay, so you don't need to erase on your paper, just watch, because this is how I'll do the next one right away. So my subscripts, I count 2 and 2. Over here, I count 2 and 1. I know that my problem is oxygen, right? It says that I only have 1 oxygen here, and those have to balance. So when I look at this mathematically, I know right away that I have to fix this. I'm only allowed to fix it by putting in coefficients. So in other words, I can't fix it like this. I can't go, okay, who cares? We'll put another little 2 there. Because what did I just turn that into? Hydrogen peroxide. I can't do that. So I put a 2 here. What did that do mathematically? Well, that changed a couple things. It made my new hydrogen count, and you always cross this out and start over. You never add to it. It made my new hydrogen count 2 times 2, 4. And it did fix my oxygen. 2 times that invisible 1 equals 2. Don't stress out. We come over here and we go, all right, so oxygen's fine, but what do I stick here to fix that problem? I need it to be a 4. Well, 2 times 2 gives me 4. And now my hydrogens and my oxygens match up. So I ended up with the same answer as I did whenever I used these models. But what's the difference is I did this all mathematically, not having to have the models in front of me. Okay, so we can use the models to get our brain thinking, or I'll show you that, but we can also do this mathematically. Okay, so I'm going to do the next one as well using both models, but just show you again how to do it mathematically. So why don't you attempt to write this equation down, push pause, try to write the equation down. I'm going to have it up here, and then you can do a check. So push pause right now, try to do number 2 where it talks about solid potassium, and then unpause and see how you did. Okay, so if I do just model talk first and we match it this way, okay, that can be our potassium. I'm going to use different colors. I'll use Michigan blue and green. I mean blue and yellow. Let's let this be our water. Okay, so my H's are blue and my oxygen. And I can only, so my goal when I think model-wise is I want to get all of these over here. But I can only add, if I need to add more, I have to add it in the way that I see them here. Okay, so it's going to make K, O, and H. So remember my H's are blue. I'm kind of saying this more to myself than you. So K, O, and H, and I'm already stuck. Okay, so what do we do? So we for sure need to add, because we're trying to make H2, we for sure need to add another water. So let's do that. So I said my waters were, or we're trying to make another hydrogen, I should say, sorry. So that was a water molecule. And why did I do that? Because I'm trying to make H2, okay? So now I have enough where I can make this H2. But what's the problem? Well, the problem is that I still have this left over, and I don't. My goal is I want to have all of this over here. So what do? Remember potassium was red? So I added another red one. And just before we backtrack, let's make sure we understand what we did. We now have added a second potassium, and if you remember, we added a second water. So now we added another one of those, which made us make or create another potassium hydroxide. So I only ended up with one hydrogen, and you don't have to write that one in there, but just to see it. And I produced also 2 potassium hydroxides. So that modeling is showing us what's going on. But again, you're not always going to have, or you don't even right now, have models in front of you. So we have to do this mathematically as well as to what happened. So let's write this down. So we have K, O, and H. And I'm going to erase these coefficients. We're going to start all over again, just so you can see how do we arrive at those same numbers. My initial count on the left-hand side, 1 potassium, 1 oxygen, 2 hydrogens. On the right-hand side, I have 1 potassium, 1 oxygen, and 2 plus 1, so 3 hydrogens. We know that hydrogens are the problem, right? And I don't know what to do, but I just know 2 and 3 can be a little complicated. We don't want to go crazy and all of a sudden up it. Take it one step at a time. I would always just, if 1 didn't work, go to 2, unless it's really obvious you need this to be a 3 right away. 1's not working, so I'm going to go to 2. So what does that change over here? Well, it made my new hydrogen count completely start over. You're never adding these together. New hydrogen count 4. My new oxygen count 2 times invisible 1, 2. Go back over here. Oh, it's like overwhelming a little bit. We think, oh my gosh, how am I going to solve this? Don't even know what to do with that oxygen right now, but maybe I can see this, or with my hydrogen, but I can see I can do a fix with my oxygen. So I stick a 2 here. What does that do? Well, it changes my potassium, 2 times invisible 1, 2. Changes my oxygen, 2 times an invisible 1, 2. And then you go, my hydrogen's still 2, but that's not right. Why is that not right? 2 times invisible 1, 2, plus the H2 over here. So don't forget that. So 2 times 1 is 2 plus that. So this actually becomes 4. And it's starting to look pretty good. Oxygens are good. Hydrogens are good. All I've got to do now is stick a 2 in here to fix my potassium. So what you got to get good at is balancing this without getting to use models. The models are kind of fun to see how they balance out, but we have to do that without using models. So let's try. I'm just going to go through all. If you're feeling good about this, then great. But I know this might be a little bit of a longer lesson. But I'm just going to go through all of this so that you have good practice videos for it all, so you can take a look at it. Now, for number 3 in the back, we would have to tell you the formula of glucose like we did. So C6H12O6 says that it combusts with, and it probably even told us gaseous oxygen. So we want to show, as much as that sentence tells us, we want to demonstrate that also with our notes so that they can see, so that we're demonstrating all of the knowledge that we have. It says that it makes gaseous carbon dioxide and then also water vapor. And remember, water vapor means it's in a gaseous form. I am really hoping that you guys can see this well. If not, then you need to tell me in the next Google Meet that you cannot see it. All right. There. This is manual Zoom. Okay. So sorry, adjusting. All right, so whenever we look at this, I'm going to do that same thing. I'm not going to use models this time, but right away, I'm just going to write out my 3 elements that I'm trying to balance. And we'll start counting. So carbon, 6, 12, and then 6 plus 2, 8 oxygens. Over here, 1 carbon, 2 hydrogens, 2 plus 1, 3 oxygens. Now, this is called a combustion reaction, a hydrocarbon combustion reaction, and I will tell you that you want to balance it in the order of the elements. It's going to be easier. So worry about your carbon first, then hydrogen, and then oxygen. tends to be saved for last. And they at first can seem intimidating, but they're really not too terribly bad. So if we just worry about carbon first, what am I going to put here to fix my carbon? And I should be able to put a 6 here, right? So what does that do? Changes this to 6. It changes nothing with my hydrogen. It does change my oxygen. 6 times 2 is 12, plus this 1 over here becomes 13. Notice how I totally mark out and start over. Okay, remember what I said, balance and order of how I wrote it, carbon and then hydrogen and then oxygen. So I'm gonna do my hydrogen next. I have 12 over there. This is the only place I find hydrogen. So I'm gonna put a 6 there to balance that. Makes my hydrogen count become 12, 6 times 2 is 12. It makes my oxygen count become 6 times 1, so 6 plus 12. So I have 18 over here. So now I want to go back on the left-hand side. Everything's looking good except for my oxygen. Now don't make a mistake and write a 9 here and go, okay, we're good to go, because you still have this 6 in this case from the oxygen. So what I do in my head is I think 18 minus 6, right? 18 minus 6 is 12, right? So if I can make this oxygen a 12, I'm good to go. 6 times 2 is 12, plus 6, 18. Okay. We're just going to keep practicing. So now these last two want you to, it already gives you the equation. It does want you to balance it. But then here's what I mean, where we're not going to let you guys give up on nomenclature. You're going to keep seeing it. So in this case, we have HCl plus copper. And they're giving us states of matter as well. And it turns into CuCl2 and hydrogen gas. All right, so let's write it out. Like I said, you always write it out by the element. Hydrogen, we have 1 hydrogen, 1 chlorine, 1 copper. Over here, 2 hydrogens, 2 chlorines, 1 copper. This one's kind of been an easy fix. Coefficient of 2 fixes everything that we need. All right, what would we be writing for this? Well, I want to use my states of matter and practice with nomenclature. Aqueous hydrochloric acid. And nothing wrong with you guys pausing, trying to do this on your own, and then coming back and checking your answers. So aqueous hydrochloric acid, I'm going to abbreviate reacts. Reacts with solid copper to produce copper 2 chloride and hydrogen gas. So again, what we mean with you're definitely going to have practice with nomenclature, both sides, reading it, being able to write it, or having the chemical formula and put its name down. Okay, so I'm going to do the last one as well. Again, you guys push pause as often as you want. I know I'm going quick, but that's because you have the ability to pause if you need to. And I got to do another flex session. So I'm trying to record this fast in between flex sessions. God, I hope I'm not late. I might be late. I'm going to have to look. I have no idea. I'm going to do this quick. Gosh, I hope I'm not late. All right. So this last one, iron. So we have iron solid plus water liquid yields Fe2O3 solid plus hydrogen gas. Okay, I'm freaking out a little bit. I think I'm late. Hold on. Oh, no, I'm good. I got to 12:45. I saw 11:45 or that it was past that. I thought, oh, shoot, I'm bad. Okay, so let's do the same idea. Fe, H, and O. Again, I like writing them in the middle because I like to save dry erase markers. Why write these things twice? So just stick it right underneath the arrow, and it's going to be easier to see everything in my mind. So 1 iron, 2 hydrogens, 1 oxygen. Over here, 2 irons, 3 oxygens, 2 hydrogens. Ooh, I like this one. Remember that first clue when it said don't try and balance the elements first? Because that's easy. I put a 2 there and it did nothing to help my scarier issue. So worry about the water, okay? So, I look here, my hydrogen's okay, my oxygen's freaking me out a bit. Now, the only number I can see that might make sense to fix my oxygen is a 3 here. So let's do that. What did that turn this in? 3 times 2. So 6 hydrogens, 3 oxygens. Awesome. Come over here. Let's fix the hydrogens. How do I do that? Let's stick a 3 here. Turns that to 6. Oh my gosh, this is looking great. Iron. How do I fix this? No biggie. 2. I'm good to go. All right. What would we call this? A good push pause. See if you can do it on your own. Then come back and check your answers to mine. What I would say is solid iron reacts with, I'm being very detailed, liquid water. I'm going to abbreviate water. To produce, don't forget if it's a type 2, iron 3 oxide and hydrogen gas. Okay, so this is a good introduction, I think, to what you guys are doing right now with balancing. For homework, we have you guys looking at the packet number 1, balancing equations, looks like this. And we're asking that you only do odds tonight. Just do the odd problem. So 1, 3, I probably don't need to say what odds are, but every time you see an odd number, do those. We're going to have the answer key posted, but then this gives you a chance to do it, check your answers, ask questions before you're asked to do more. All right. I hope you're all doing well. You take care. If you need to reach out to me, email, we can Google Meet independently if we need to, but take care. Get outside. Miss ya.